Episode 101, titled Neural Network Basics, Neurons, Layers, and What Representation Means, we focus on understanding neural networks as layered feature builders rather than as mysterious black boxes that somehow just learn. That shift in mindset matters because networks become far less intimidating when you view them as systems that transform inputs into increasingly useful internal features. The exam goal here is not to turn you into a deep learning specialist, but to ensure you can describe what a neuron and a layer do, why depth matters, and what people mean when they talk about learned representations. In cybersecurity and data science work, you will see neural networks used in places where manual feature design is hard, such as text, images, or complex behavioral sequences. You will also see them used where they are unnecessary, simply because they are fashionable, which creates avoidable risk. This episode builds the conceptual model so you can choose networks for the right reasons and explain them in plain, defensible language. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A neuron is a simple computational unit that takes inputs, forms a weighted sum, adds a bias term, and then applies an activation function to produce an output signal. The weighted sum is the part that aggregates evidence, assigning different importance to different inputs through learned weights. The activation function introduces nonlinearity, which is critical because without nonlinearity, a network of many layers would collapse into an equivalent single linear transformation. You can think of the activation as a gate that decides how strongly the neuron should pass forward a signal based on the weighted input it receives. The output of the neuron then becomes an input to neurons in the next layer, allowing many such units to work together. This basic pattern is repeated across the network, and learning is the process of adjusting weights and biases so the neuron outputs contribute to accurate predictions. A layer is a collection of many neurons that operate in parallel, taking the same input vector and producing a new vector of outputs. Each neuron in the layer has its own set of weights, so it responds to different combinations of inputs, effectively creating multiple learned features at once. When you stack layers, each layer transforms the output of the previous one, producing progressively more abstract or task-relevant features. This is why layers are often described as feature transforms, because they take raw inputs and convert them into a representation that makes the final prediction easier. The number of neurons in a layer controls how many features the layer can express, while the arrangement of layers controls how those features are composed. In this view, a network is simply a sequence of transformations from input space to output space. The apparent complexity comes from scale, not from a fundamentally different kind of computation. Representations are the learned internal features that a network constructs as it trains, capturing patterns that help predict the target. In early layers, representations often encode simple patterns directly connected to the raw inputs, such as basic combinations or local structures. In deeper layers, representations can become more abstract, capturing higher-level regularities that are useful for the task, such as a semantic signal in text or a behavioral signature in event sequences. The key is that these features are not hand-designed, they are discovered through optimization to reduce the loss function. A representation is therefore not a label or a rule, but a set of internal signals that the network has learned to compute because they correlate with correct outputs. When people say a network learns representations, they mean it learns intermediate features that make the final mapping from input to output easier. This is also why networks can perform well on unstructured data, because they can learn feature hierarchies that would be difficult to engineer manually.
Depth enables complex patterns because each additional layer allows the network to compose simpler features into more complex ones, expanding what the model can represent. Composition is the central idea here, because a shallow network can only express limited transformations, while deeper networks can build multi-step feature pipelines.
However, depth also increases training difficulty because information must propagate through more layers, gradients can become unstable, and the optimization landscape becomes more complex.
Deeper networks also have more parameters, which increases capacity and therefore increases the risk of overfitting when data is limited or noisy. Training deep models often requires careful choices about architecture, activation functions, and regularization to keep learning stable. This is why depth is powerful but not free, because it multiplies both modeling flexibility and training complexity. Understanding the depth trade-off prevents you from assuming that more layers always means better performance. A forward pass is the process of taking an input, pushing it through the network layer by layer, and producing an output. The input vector enters the first layer. Each neuron computes its weighted sum and activation, and the resulting outputs form a new vector. That vector becomes the input to the next layer, which repeats the same computation, and this continues until the network produces the final output at the last layer. For classification, the final output might be a probability-like score, while for regression it might be a continuous value, depending on the chosen output activation and loss function. The forward pass is deterministic given the weights, meaning that once the network is trained, the same input produces the same output. Training then adjusts the weights based on how wrong the output was, but the prediction mechanism is always this repeated transform. Being able to describe the forward pass clearly is a good check that you understand the network as layered computation rather than as magic.
Neural networks are most appropriate when data are complex, large, or unstructured, meaning the relationships are difficult to capture with simple engineered features or simple model families.
Text, images, audio, and many sequence-based behaviors fall into this category because the raw inputs contain rich structure that traditional models struggle to represent without heavy feature engineering.
Networks can learn useful representations directly from these raw or lightly processed inputs, which can reduce the need for manual feature construction.
They also become more attractive as data volume increases, because large datasets can support the model capacity and reduce overfitting risk. In practice, networks are often chosen when the task benefits from representation learning and when the organization can support the training and monitoring requirements.
The exam-level principle is that networks are a tool for complex function approximation, not a default choice for every problem.
When the data structure demands it, networks can be an excellent fit. At the same time, you should avoid networks when simpler models meet the needs with less risk, because simplicity can be a form of reliability.
If a linear model, a tree-based ensemble, or a probabilistic baseline achieves the required performance with clearer governance and lower operational cost, using a network can be unnecessary complexity.
Networks can be harder to debug, harder to explain, and more sensitive to data drift and training instability. They also often require more careful tuning and more robust monitoring to prevent silent performance degradation.
In regulated environments, explanation requirements may favor models that are easier to interpret directly.
The professional posture is to treat neural networks as one option in a toolkit and to choose them only when their advantages, especially representation learning, matter for the decision outcome. Avoiding unnecessary networks is not conservative, it is disciplined engineering.
Initialization and scaling affect training stability and speed because networks learn through iterative optimization, and the starting point can determine whether learning proceeds smoothly or stalls.
Poor initialization can produce activations that saturate, causing gradients to become tiny and slowing learning dramatically. Feature scaling matters because inputs with wildly different magnitudes can cause some weights to dominate early updates, leading to unstable training and slow convergence. Proper scaling and sensible initialization help maintain healthy signal propagation through layers, allowing gradients to flow and weights to update in a stable way. These considerations are not optional details because they often determine whether training is efficient and whether the model reaches a good solution.
In practice, these are among the first places you look when training is unusually slow or unstable. Understanding that networks are sensitive to these setup choices helps demystify why training sometimes feels fragile. Networks are also closely linked to embeddings, which are learned vector representations that capture meaning for text tokens and categorical values. In text, embeddings convert discrete tokens into continuous vectors that the network can manipulate, allowing similar tokens to have similar representations based on learned usage patterns. For categorical features, embeddings can replace sparse one-hot encodings, learning dense vectors that capture relationships among categories, such as similarity among users, devices, or product types. This is a practical form of representation learning because the embedding space becomes an internal feature system that the network learns jointly with the rest of the model. Embeddings are a major reason networks can scale to high cardinality categories and large vocabularies without exploding feature dimensionality.
They also help capture nuanced relationships that are hard to express with manual encoding choices. Linking neural networks to embeddings is therefore a way to explain how networks handle discrete structured inputs in a more flexible way than many traditional models. When communicating neural networks, it is accurate to describe them as flexible function approximators with trade-offs because that framing captures both their power and their risk. Networks can approximate complex mappings from inputs to outputs, especially when they have sufficient depth and capacity, and when they are trained on enough representative data. The trade-offs include higher compute requirements, greater sensitivity to training choices, less direct interpretability, and more demanding monitoring needs. This framing avoids both extremes, which are treating networks as magic and treating them as unusable black boxes. It also helps stakeholders understand why networks can be valuable in unstructured data problems, but unnecessary in simpler settings. When you communicate networks as layered feature builders, you give people an intuitive story that aligns with the mechanics of training. That makes governance conversations easier because the model is described in terms of what it is doing, not in terms of mystique. Compute planning is part of responsible network use because networks often require significant training resources and careful monitoring during training to avoid wasted runs and silent failure. Many practical networks benefit from acceleration hardware, such as graphics processing units, abbreviated as GPUs, because matrix operations dominate training time. Even with good hardware, training can take substantial time and can fail due to poor hyperparameters, unstable gradients, or data pipeline issues, so monitoring training curves and validation behavior is essential. Compute planning also extends to inference because some networks are lightweight while others are heavy, and deployment constraints may limit what you can run in real time. In security contexts, where systems may need to score events at high volume, inference cost becomes a major factor in architecture choice. The exam-level message is that networks are not just algorithms, they are systems that demand resource planning. If you ignore compute realities, you can choose a model that cannot be trained or deployed effectively. The anchor memory for episode 101 is that layers learn features, features drive predictions, and training shapes them. Layers transform inputs into internal features, and those features are what make the final prediction possible. Training shapes these features by adjusting weights to reduce loss, meaning the representation is not fixed but learned through optimization. This anchor keeps your focus on the mechanism rather than on the mystique, and it explains why networks can succeed where manual features are hard. It also implies why data quality matters so much, because poor data teaches poor representations regardless of model power. When you remember this anchor, you can explain networks as a feature learning pipeline rather than as a black box.
That explanation is often enough to satisfy exam questions and to support professional communication. To conclude episode 101, titled Neural Network Basics, Neurons, Layers, and What Representation Means, describe a network in one sentence and then name one trade-off. A neural network is a sequence of layers where each layer applies weighted sums and nonlinear activations to transform inputs into learned internal features that ultimately produce a prediction. One key trade-off is that this flexibility often requires more compute and more careful training discipline, and it can reduce direct interpretability compared to simpler models that produce clear coefficients or rule lists. If you add that networks are best justified when data are complex or unstructured and simpler models are insufficient, you show you understand model choice as an engineering decision. This one-sentence description and trade-off capture the core idea without drifting into unnecessary detail. When you can state it this clearly, you demonstrate exam-level understanding of what a network is and what representation learning means in practice. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.